Hello everyone, this is Monica. Today I'm here about to talk about Diffie-Hellman key exchange algorithm. Diffie-Hellman key exchange algorithm is mainly a asymmetric cryptographic technique, which means that here we are going to use a pair of keys. One is a private key, another one is public key. Here, the main purpose of the Diffie-Hellman key exchange algorithm is that to exchange the secret key between two persons, like user A and user B, they are going to exchange the secret key between them for the encryption of the messages in a secure way. That's the purpose of the Diffie-Hellman key exchange algorithm. Here, for this algorithm, here we are mainly using two global elements. One, a prime number, and another one, an primitive root of P, means which these two are global elements, so that everyone in that network can know these two elements. How to generate, what is the process in the Diffie-Hellman key exchange algorithm? Mainly, we are here going to follow the two steps. One is key generation process, and another one is computation of the secret key, which is shared between the two members. Suppose let's think that there is a user A and user B. Here they are going to exchange the secret key. Before that, they need to generate a set of private keys and a public keys. Now let's see here a generation of the public key between generation of keys for user A and generation of user for B. This is, as I told that Q is a prime number, here we are considering. X1, XA is a private key. Here we are going to select a private key, which is randomly, which we are going to select a random number. And similar to the B side also, we are going to select a random number XB, and we are going to compute YA and YB by using a formula alpha power XA mod P, which is nothing but we are using primitive root power of we are going to take the private key and mod of the prime number. In this way, we are going to calculate our public keys with the help of the private keys. Here now we can see that XA, XB are the private keys of this, and YA, YB are the public keys. Now we are going to compute the secret keys. Secret key between user A and user B. And we are going to calculate the secret key individually for user A and user B. Now this is how we are going to compute user A side secret key. K is equals to YB power of XA mod P. And user B side, we are going to calculate the secret key with the help of X is equals to YA power B mod P. In this way, we are going to calculate the. Now, the most valuable thing is here that both K values will be the same, and they are going to share the same secret key, but they are going to compute individually. That's the beauty in this. And how the secret key will be same. Now, let's see here. Let's consider here we are taking the user A side secret key generation. That's what I have considered Y power B. Here I'm considering this. As we all know that YB is equals to alpha power XA mod P, because we computed here, right? That's what we are going to consider here. And we are just doing some modular arithmetic operations so that we can have some calculations, and we'll finally get that secret key that is generated between KA and KB will be both equal, so that the secret key in generation will be same. That is what we have to note. Let's see a small example over this. As I told that P is a prime number, that is we are going to see, and 23 is a prime number, as everyone know that. And alpha is the primitive root of the 23. And these two will be given by, these two are global elements. These will be given already. Now now we are going to generate the key generations between user A side and user B side. Now we are having XA is equals to 4 and XB is equals to, these two numbers I have chosen randomly. Now for these numbers, I have to calculate YA, which means I am going to calculate the public key. Alpha is equals to XA mod P, right? I have already told that the formula. So 9 power 4 mod 23, and 9 power 4 is nothing but 65261 mod 23. The final answer we are going to get is 6. And again in YB is equals to 9 power 3 mod 23, which is nothing but 9 power 3 is 729 mod 23, and we are going to get as 16. Now, XA is equals to 4 and XP is equals to 3. These two are the private keys, and YA is equals to 6 and YB is equals to 16. These two are the public keys. With the help of these keys, we are going to compute our secret key. Now let's see the secret key calculation through user side A. secret key XA is equals to YB power mod AP. So 16 power 4 mod 23, which is 16 power 4 is nothing but 65536 mod 23. The answer would be 9. And the secret key generation in the either side of the B is nothing but KB is equals to YA of power XP mod P. 6 power 3 is nothing but 216 mod 23. Here we are going to get test 9. So now finally we have both secret key generations from either sides of user A and user B is equals to 9. So our secret key here is 9. The main drawback of Diffie-Hellman algorithm is man in the middle attack. So someone is going to be in between user A and user B and going to observe the messages, encrypted messages and messages, what going on between these two, and they are going to steal those messages, or they're just going to override them or something like that. This is what we are going to discuss now. It's nothing but MIMA. Here, let's consider this one is a user A and user B. Here, the intruder will be, and he is going to steal the data between user A and user B, or otherwise, he's just going to going to misuse the data between these two. Now, how the steps in the MIA would be, I'll just going to say that. Here, intruder first, he is going to generate two private keys, X1 and X2, and he is going to keep them, and then he is going to compute the public keys with the help of these two private keys. As I already told that alpha is nothing but primitive root and the P prime number both are global elements, so that would be known to everyone. So intruder, with the help of these elements, he is going to come into the communication circle between A and B. Now intruder computes the both y1 and y2, which are public keys. Y1 is equals to alpha power x1 mod p, and y2 is equals to alpha power x2 mod p. In this way, he is going to calculate two public keys. Now, when user A is going to send his his public key to the B, middle user, intruder will come and he just passes his own public key to the B. Let's see here. User A sends a message now. User A is sending here. YB he is sending. In between, this fellow is going to stop that YB and he is going to collect that YB, and he will send and he already generated Y1, right? That Y1 he will send it to B. This is what he is going to do. Again, after that, and what Bob will receive now? Now Bob is going to receive this Y1. He is thinking that the received public key is from user A. Intruder also now intruder's second part is to calculate the secret key which is shared between user B. That is what K2 is equals to YA power X2 mod P. Again, same thing happens to the user B. When user B sends his public key to the user A, intruder again interrupts and he takes that YA and he will passes Y2 to the user A person. Again, intruder also calculates the X1 and K1 and K2. User as I told that there will be another second secret key between user A and user B and intruder. Now, mainly user A is going to have the secret key K2 between intruder and the user A, and intruder is going to have K1 secret key between user B and the intruder. Now we have two set of keys, K1, K2 and K1, which are shared between user A, user B and intruder. MIMA mainly have two types of keys, one pair of key and two pair of keys. When one pair of keys is nothing but when K1 and K2 equal and K1 and K2 are equal. K1 and K2 will be equal in only the one condition, when Y of A, that means public key at the A side and public key which is generated by the intruder, a set of public key are equal. And again, public key of B, user B and which is generated by the intruder, both are same, then we are going to have this one pair of keys condition is possible. Otherwise, in these two pair of keys, there is no possibility of getting. So the two secret keys generated between them are different. This is my this is what I from here I'll conclude.